done on chatbot detection with my colleagues at the Air Force Research Labs, my wife Lindsay, and Dr. Paul Hadley and Kate Ferris. We're all contributors. And I should say we all are psychologists by training, research psychologists, and Kate Ferris in particular is a mathematical psychologist. So a little bit different background than most of you guys, probably in computer science. But we're interested in chatbot detection for the purposes of cybersecurity and the potential threat that chatbots can pose to unsuspecting users. They can spam and conduct phishing attacks and spread malware, as we all know. And there's even reports of them doing social engineering. So I have a couple of these news articles that you might have seen talking about how people got tricked into giving 200 grand into chatbots. And Dr. Epstein's article about how he got tricked by an email chatbot that he thought that he had met on a dating service. So it's all very interesting. But potential security issue there, which is why the Air Force is interested in it from a research perspective. So there's two different types of bot detection I'm going to talk about. There's the active, what you guys probably think of, where you're interrogating a bot one-on-one. So what we wanted to do was look for some active methods that might be able to be used consistently and reliably in detecting a bot. Or in other words, what kind of questions should you ask a bot if you want to out it? The other type of detection is passive or automated, and this would be where a computer could do the detection for us to say whether it's a bot or a human. Particularly, we look at message features like the message sizes and the intermessage delays in the chat data, but I'll get to that eventually. So for active detection, the problem is essentially the Turing test problem. The interrogator has to decide if another communicator is a bot or not. So we performed a Turing test literature search and looked for what people thought, what should you ask during a Turing test, the Turing test to out the bot. So we wanted to provide like a strategy guide or a big compilation of types of questions, because apparently no one had ever done this before, just to see what we find. First thing we found was disheartening. Bertel was saying that there is no surefire strategy for the Turing test. But of course we went ahead anyway and continued with our literature search. The first initial hints we came across were that good probing questions should obviously require demonstration of understanding or thought, complex thinking on the part of the bot or the communicator. In particular, Floridi and his colleagues say that your questions should require informative answers. They shouldn't be like the magic 8-ball type questions where you're just going to get a yes or a no or a maybe. So do you believe in God or do you like cheese? It's not going to be very informative as an interrogator to ask these types of questions. Moore's a little more specific in explaining that what he calls URL questions should be useful. So these would demonstrate either understanding, reasoning, or learning by the bot. Understanding would be asking and ensuring that the bot can figure out logical type questions and reason through problems, and that it can demonstrate that it's learning from your interaction. Floridi and his colleagues again talk about elementary logic and making a bot demonstrate that it knows very simple logical type questions and can answer them. He also suggests using common typing shortcuts that are hard to program potentially into ahead of time, so that but that people have no problem reading. So, do you go to dinner before you go to see a movie? Potentially, you could use figures of speech or slang to out a bot because a bot would have trouble interpreting what you're asking. And this was one of my favorites, was requesting the bot to enumerate the function of things, the functionality of different things. And you can think of anything besides a tennis ball, a telephone or a fork. Or, a bot should have problems doing such tasks, theoretically, is what we're thinking. Another idea is to use ambiguity probes. So in this case, you would you're basically hitting the bot with ambiguous questions or ambiguous problems to work through. So if you give them intentional misspellings like this, can you read these words that I've typed? Humans have almost no problem being able to read those. And yet a computer would potentially have difficulty if it wasn't programmed well. You could ask it blank questions just to see what, how the program responds to that. It's a blank input. You could potentially ask just word gibberish where you're typing letters, or sentence gibberish where you're typing complete words, potentially even in grammatical structure. That would make sense, except for the fact that when you put the whole thing together, there's no real underlying meaning. So when you hit the weather, dog, and the moon, just the president sing blue on Sunday, that's all structurally correct and grammatical, but it just doesn't make any sense. So potentially a computer would be able to pick up on that. A few mistakes that chatbots seem to make that might tip you off that it is a bot is they tend sometimes to repeat things exactly in a way that humans would be very unlikely to do. And this is one example from the Lebanon Prize data. Another is regurgitation. It's where they repeat back something you said in a way that a human would be unlikely to, especially like, did George Washington free the slaves? Obviously, it was a trick question, but the bot regurgitates that right back to the interrogator, and he even does the misspellings and all. One of the earlier talks talked about the keyword targeting that bots are likely to do. So potentially this could tip off an interrogator that they're talking to a bot if the bot seemed to be steering the conversation to limited topics. Or if they're evading topics that maybe you would like to talk about, that could be a tip-off. So a couple examples of invasion here are, the chatbot comes up with an excuse saying why they're not going to answer that, or they just, turn the question on the interrogator, which is pretty interesting. So Pertal might potentially be right. There's no surefire strategy for active detection, but our hope was that we could compile at least, or get started compiling some strategies that might help provide some confidence in outing a bot for potential security purposes. So I'll move on to the passive detection work that we did. The only previous work that I could find on this was by Gianvecchio and his group at College of William and Mary. So they looked at over 1,400 hours of public logs, and they went through by hand and they classified everything as either a human, a bot, or an unknown message. And then they threw out all the unknown and compared the humans to bots on these two particular communication features. So their intermessage delay times. If I said hello, how long did it take for the bot to say hello back? That's the intermessage delay. And then the message size that they measured, particularly in bytes. They chose these measures because we know from a whole wealth of data that humans exhibit very distinct temporal patterns in their communication, and potentially it was possible that they would exhibit message size patterns. So they wanted to see if that would hold true and add a distinguishing feature. So here is the probability density distribution for the humans, and you can see a very clear pattern here in terms of the intermessage delay times. And this is analogous to Zipf's law, where we see in all forms of human communication, pretty much, you see a nice clear relationship here, and these are log scales. Here on the message size, we see not a similar pattern, but a distinct pattern also for the humans. For bots, this wasn't really true. A particular type of bot that they identified in their data was called a random bot, and the two colors here represent two different months of the data that they're looking at. And you can see there's just not clear patterns, and even if there is a gross pattern suggestible, maybe in some of this data, it's certainly not as clear as it is here for the humans. And then here in message sizes, the rate in the bot was just all over the board. So they found that based on these simple metrics, they could classify bots essentially into 14 different behavioral types, like periodic and random and replay. But really what they were doing was looking just in chat rooms for bots that were trying to trick people into clicking on a hyperlink. That was either they would post or that hyperlink that was posted in a profile. So they weren't really trying to carry on very long conversations. They weren't trying to trick people necessarily into thinking they were human. More along the lines of the main goal would be click on a hyperlink and download this unsafe file or whatever it might be. And again, they found that there's distinguishing metrics in both cases were intermessage delays and message sizes. So we wanted to build on this work, and we wanted to apply it more to instances instead of group chat like the Yahoo chat rooms. Look at one-on-one IM types of chat where the bots are potentially trying to carry on a lengthy, convincing conversation. So we looked at the web enterprise data, only 5 years worth, because for this particular analysis, these years had very easy transcripts to analyze. So we looked obviously at the intermessage delays and the message sizes. This time we used message size. We defined it in terms of word count instead of bytes, and that was just a judgment call on our part. And then we also did a combined measure of these first two called message rates, where we divided the size over the delay times. So it's roughly analogous to typing speed, although not exactly. So from these metrics, we measured central tendencies, we measured distribution shapes, we measured the complexity using entropy and entropy rate. And what we found was, in terms of intermessage delays, humans were different than the bots on all these particular measures. So the central tendencies, the variance, and the distribution shapes.
Sorry, but that's something that can be easily verified.
Yeah, I'll get to that. I agree. And here's what the distributions look like. So this would be the human distribution. It follows another clear pattern, just like we would expect. And then the bots have a very distinctly different pattern. In terms of message sizes, we found only that kurtosis was noticeably different. And kurtosis is a particular measure of the distribution shape. And you can see here that the curves are very similar between the humans and the bots. In terms of message rates, again, we find a large difference in all the measures between humans and bots. And the distributions look like this. There's a huge spike here for the humans. This indicates that almost all the humans answered between 0 and 100 messaging rates, which isn't very surprising, but the bots were all over the spectrum here.